Hello, everyone. My name is Dan, and I'm the chair for this session. Welcome to this session. We have two live sessions, two live speakers in this session, and the third session has been pre-recorded. So you will, in the end of the two presentations, you will need to end this call and go back to the timeline to watch the pre-recorded session. The first speaker for the session is Dr. Pablo Higuera. He is a lecturer in the coastal engineering at the Civil and Environmental Engineering Department in the University of Auckland. His research field is computational fluid dynamics applied to coastal hydrodynamics, wave structure interaction, and hydraulic and environmental flows. The topic of his talk is parallel CFD modeling to explore scale effects in coastal engineering wave structure interaction simulations. Let's welcome our first speaker.
Thanks, Dan, and kia ora, everybody. Share my screen and start the presentation. Yeah, so thanks for the introduction. Today I will be talking about a research topic that I've been carrying out for a couple of years in conjunction with Professor Liu in the University of Singapore. And it's on CFD modeling to explore scale effects in coastal structures, in this case, slip breakwaters. So the outline of the presentation is as follows. I'm going to start by motivating the topic a little bit. This is a very brief presentation, so I'm going to scratch the surface only in all the topics, but feel free to ask any other questions in the end. I'm going to revisit then a theory, a very beautiful theory, almost developed 30 years ago. And what can we do with CFD to kind of enhance this theory nowadays? So today I will be talking about perforated breakwaters. And perforated breakwaters, you see an image of over there, are basically caissons that you build ports with. And they include like a porous part. So they're very, very effective in reducing wave reflections, and that is their main advantage. Normally, if you place a wall in a harbor, it will reflect 100% of the energy, and then the energy would just start building up and creating waves. So your vessels won't be safely moored in these caissons. That's why in 1960s, research for creating some kind of structure that is more efficient in dissipating wave energy was created. And they developed these perforated breakwaters, or also called Jarland breakwaters. The physical limitation for how they interact with waves is, of course, the length of this resonance chamber that they have between the caisson, the vertical wall, and the porous revetment. So how do they work? Well, they work to reduce agitation by two means. First one is by dissipating energy. So energy gets through this porous medium and you have some laminar waves. If you have higher waves, you get into the turbulent regime, and obviously you experience, or water experiences, friction and shear, and that reduces the amount of energy. But the most interesting part is wave interference. So basically, they have a resonance chamber in which energy is able to flow in and out, and that creates phase shifts in the waves and additional harmonics, and that is the really interesting mechanism that is able to effectively reduce wave reflections. So we were thinking about revisiting formulation developed almost 30 years ago, because this formulation was very, very simple and very beautiful. You're going to see in the next slides. So the original experiments dealt with slit caisson breakwaters. That means different columns placed on front of a reflective wall. They were performed in Osaka, and they were at 1:50 scale. So each of these cylinders, or these square cylinders, is 5 centimeters, which roughly represents a real structure that could be built 50 times larger. And this theory was developed using potential flow, so it has some limitations, but it is very, very good because it provides a way to calculate the reflection coefficient that this breakwater provides without scale effects, meaning that all the terms included there are dimensionless. So that means that irrespectively of the scale that you're applying, you will get always the same result. There is only one catch there, and it's a single tuning factor, F, which corresponds to an energy loss coefficient. The best value was found 1 year later. It is 1.5. And this is kind of the only term that might tell us whether we have scale effects or not. This term was calibrated for laboratory scale, and in the next slides, we're going to see whether it holds for all scales or not. So as I said, this theory provides a curve so that you can calculate the reflection coefficient for your structure, and it's validated in the lab. So each of those dots that you see over there is some experiments that they run in Osaka. And as you can see, the matching between the theory and the experiments is excellent. And that made us ask some additional questions, because when you're running physical experiments, you cannot test all the conditions because they take some time. You need to wait between experiments for the waves to settle down. So they only tried one wave steepness, and that is the ratio between the wave height and the wavelength. And that's a very small value. And the theory does not point out any scale effects. So we're asking what is the impact that turbulence will play for larger scales? We're going to see that later. And whether is this factor F affected by scale effects because it was calibrated for just small scale experiments. So in doing so, I'm using OLAFlow, which is an open source numerical model that I've been developing for some years. It is based on OpenFOAMs and solve the 3D Reynolds average and Navier-Stokes equations for two incompressible phases. So we can deal with free surface waves because we have air and water. We include also different ways to generate and absorb waves actively at the boundaries, and lots of different turbulence models like K epsilon and K omega, or even going into LES. So we started by replicating the experiments exactly with the same setup, exactly with the same scale. And we also decided to test the same experiments, but in larger scales. For doing that, we use the K omega SST turbulence model, which is proven to be accurate for simulations with dealing with waves. And we came up with a structured mesh, which is a very, very simple mesh and has 1.3 million cells. For each of the experiments, we run one simulation around 30 to 40 wave periods long. And that took 12 to 60 hours using 16 processors. So these simulations are manageable and you can run them even in your workstation. And then we decided to scale things up. And since we were running like 1/50 scale experiments, we decided to blow everything 50 times in space. And usually when we're dealing with hydraulic simulations, we apply fruit scaling. Fruit scaling basically ensures that the inertial and gravitational forces are balancedly scaled up and down. So that means that if we blow everything 50 times in space, all the cells will have 50 times the size in the small scale. We need only to increase time by 7 times. So it's kind of a not balanced way to scale everything, but it is how it is. These are the results for one wave period. So as you can see, we get our very small waves reaching. We have the resonant chamber, which is reflecting, it's going back and forth, and you see some very nice vortex shedding which is also contributing to dissipating energy. The results, as compared to the theory, match perfectly, both at small scale and at large scale. The agreement is as good as they found in the lab scale. And we're able to, with these simulations, find very interesting effects. As for example, this resonant chamber is doubling the effective frequency of your waves. It's generating waves not with the same frequency as the generated waves, but is also transforming energy and creating a second harmonic. So you can see the rect signal over there has 2 peaks rather than 1 that you see in the blue signal. But that pointed no scale effects, and our research would end there. Nevertheless, we wanted to go one step further and ask ourselves, like, yeah, we're applying fruit scaling, but what happens with turbulence? So if you apply a length factor of 50 times and a times factor of 7 times, what we're doing to turbulence is actually blowing up by a factor of 350, and that's massive. And that makes that the mildly turbulent or even laminar lab scale case with 22,000 Reynolds number blows up to 8 million. So the laminar case suddenly becomes a very, very turbulent case. That has some other implications, and is on CFD we have the Y+, and Y+ is basically telling us where our first cell close to the cell is with respect to the viscous or the boundary layer. In the lab scale experiments, we are at the value 12, which means that we are very, very close to the viscous sublayer. And in prototype scale, we are now at 3000. And at 3000 means that we are very, very far off. We're not simulating, or we're not solving the boundary layer. And on top of that, the K omega SST turbulence model is out of the applicability range. The applicability goes up to 300. So we're almost 10 times higher. That made us think, oh, what happens if instead of getting like the original scale and having our cells 50 times bigger, we make them smaller? So that means that we have 10 times more cells. We're now with 13 million cells, and we were able to lower down the Y+ to 475, which is closer to the range of applicability. And that means that we suddenly need to use high performance computing. And this is where NeSI comes as a cornerstone for this project. So with 144 processors simulating 100 seconds, which is kind of the equivalent of the previous simulation, takes 5 days. So we're able to run kind of the same cases, but with additional simulation and get additional resolution and get more information. The first findings, this is work in progress, so this is just preliminary results, were puzzling. So previously we were obtaining 13.6% reflection coefficient, whereas now with larger number of cells or high resolution, we get 40% reflection. That means that our structure is reflecting 3 times more than we were expecting, meaning that if you test this structure in lab, you may expect 13% reflection. Suddenly you build it in real life and you're up to 40%, which is probably not what you expect or what you want to prevent your more vessels to stop rolling. And we were able to see some very noticeable differences. So here is a case in which the resonant chamber is producing some discharge into the seaward side. On the left, you have the regular resolution at prototype scale, and on the right, you have the high resolution simulation. So you can notice some very noticeable differences. There is flow separation happening because of the smaller cells. So we can capture more detailed phenomena. And this is basically occluding some air and creating some vortices that cannot be represented for the larger cells. Here is another view from the top representing the streamlines, and you can see the flow separation over there. So we still need to perform more simulations. We still need to characterize what's going on a little bit better. And we're going to do that in the next year with some allocation that we had just been granted. But what our thoughts are that this flow separation is basically reducing the effective gap distance. And this formulation is very, very sensitive to the gap between each column. So that's probably why we get 3 times as high reflection coefficient as we were expecting. And just some conclusions before closing. The theory that was developed 30 years ago is simple, it's very beautiful, and it's powerful. It represents reality very well, but it may not be that useful to extrapolate to real life. With CFD, we proved that it worked, but we want to see what happens in the next step. And how are we going to do that? Well, we're going to explore additional cases, probably trying to fit a new F value to see if the F value is affected by scale effects. And we want to at least run one additional simulation pushing the resolution higher so that we can see like all the different effects and even going into LES simulations. So this is all for today. Thanks, and if you have any questions, I'll try to answer them gladly.
Thank you for this very interesting talk. Looking at the live Q&A session, currently there's no question there. So I guess, well, I do have a question actually. Now you know that at scale, the simulation is, your new simulation is telling you that the old simulation is not that accurate at scale. Does that actually impact how we build large, infrastructure in real life? Since the old way of thinking isn't quite correct. Obviously, I guess people have observed them in the past to find the differences, but now you can through simulation, you can find the delta, the differences. How would it help us to build better structure in the future?
Yeah, so scale effects is something that is there. It's always there. You don't know how they will impact your structure until you build it, unfortunately. There is some information because obviously these structures have been built since the 1960s. So observation in real life and even large scale physical simulations, which are costly but are also another option to perform, are the way forward with this. Now with CFD, we're kind of extrapolating things because we have validated the code for small scale and we hope it works for large scale. But actually we cannot try or test our hypothesis until we build this thing like full scale. Right.
We have one question from Alexander Plexer. We have 40 seconds to answer it. Is there any relationship between this work and electromagnetic materials, which are based on periodic structure and which exhibit exotic reflection properties?
Okay, it's the first time that I've heard about such a thing. Probably not. This structure is completely static, so there is no flexibility at all. It is made out of concrete, and it basically relies on resonance. So it's a very, very much simpler probably than metamaterials.
All right, thank you. We have to move on to the next session. Thank you, Pablo. So the next speaker, Wolfgang Hayek. He is a research software engineer at NeSI and NIWA. He is also a group manager for NIWA's scientific programming group. He has many years of experience in scientific computing and high-performance computing. And the topic of his talk is parallel computing with Dask. Here we go, Wolfgang.
Thanks, Dan. All right, I'll share my screen. Okay, I hope you can see the presentation. Yeah, thanks everyone for coming along. Today I'd like to talk a bit about the Dask toolkit, which I found quite amazing. As often with talks that I give at conferences, this comes out of a consultancy project. So I'm working as a NeSI consultant to some part of my time. And in this case, I worked with Jan Schindler from Manaki Finnow Landcare Research on a machine learning workflow. And that was the first time I used Dask. And I found it so amazing that I thought I'll give a talk about it. So it's mainly an overview talk, but I'll talk also a little bit about this particular application. And also to mention my colleagues Maxime and Chris. So Maxime recorded the demo that you can see after my presentation. So he'll go into a bit more detail about some aspects of Dask. Okay, so at first I'll start with an overview of what Dask is in case you've never heard about it, or if you've heard about it but never had a chance to have a look at it yourself. I think it's fair enough to call Dask the Swiss Army knife of parallel computing for Python, at least, because there's an amazing array of APIs that you can use. I'll discuss it in a moment in a bit more detail. And so it should cater for a lot of use cases for work that you can do in parallel on modern multi-core computers or cluster computers. Then speaking of clusters, if you're interested in HPC, then Dask MPI is something for you to look at. And we use Dask MPI for this consultancy to speed up that workflow. Then I'll briefly touch on containerization. So often, I guess, Dask is used for data processing, which usually requires additional dependencies, and containers are quite a good way to deal with such dependencies. There's a bit of thought that needs to go into creating a container with Dask. So that's why I'll briefly touch on that and then finish with the summary. All right. So Dask is indeed a Python toolbox. I think it's the basic Dask toolkit. It's completely written in Python, so it uses a lot of onboard Python features to do its job. But the real beauty of Dask is, so for its parallel processing, it completely abstracts out the API, so the kind of programmer-facing parts of it from the backend that actually implements the parallelization. So that distinguishes it from many other parallelization toolkits or parallelization APIs, like if you might have heard of MPI or OpenMP. Where you really have to work quite close to the low-level aspects. In Dask, you don't have to do that. So you get an API that is completely abstracted. So in principle, you don't care if at the back end Dask uses multi-threading, where you use multiple cores inside the same process, or where you use multi-processing, where you use the message passing interface MPI. There's a way to do this with Slurm as well if you're on the HPC. In principle, you don't care. Now, in practice, this looks a little bit different because each of these backends have a few things that prevent this or that in your workflow. So you'll sometimes run into collisions with that. So not everything is completely portable, but in principle, it should be largely portable between these different backends. And at the same time, these backends allow Dask to be scalable from laptops to clusters. So you can start small if you like. If you only have a moderate amount of data to process, for example, you can happily do that on your laptop, and you can use all cores on there. And if you then realize, okay, laptop's not enough, I need to go large and wide, so then you can just carry that over to clusters, use a different backend, or you can go into the cloud and run it there. So in terms of the APIs, there's direct integration that Dask offers with very well-known Python packages. I mean, you'll all heard of NumPy, of course, then Pandas for data analysis, data processing, and scikit-learn. And that's really the complete lazy way of implementing parallelization. There, often it's enough to just do an import Dask, and Dask then integrates with the well-known objects that these packages give you, like ND arrays for NumPy that you can now run and operate on in parallel. You can just use the usual methods for adding, subtracting, averaging, whatever you have, and Dask does all the parallelization effort at the back end, so you don't actually have to do anything. Same with Pandas for data frames, or for scikit-learns for the different machine learning engines that also integrates nicely with Dask. I'll go into a bit more detail now about the low-level APIs. So that's when you actually have to think a bit more about how you implement parallelization. And Dask has two different kinds, which are called delayed and futures. So this is the example that you'll find if you go to dask.org on the web. So I didn't use that myself, so I'll just give you the gist of this. If you listen to Hillary's talk earlier on, Dask delayed is a bit like Silk, just much simpler and of course not anywhere near as powerful and as sophisticated. But what that does is basically it gives you the ability to create a data processing pipeline by just creating Python functions, as you see here, just in a very simple case, of course. So a function that increments a number, a function that adds two numbers. And so you hand over that function definition and the input to the Dask delayed package. And Dask delayed in the background constructs a dependency graph out of that that you see here in the top right corner. And so in the real world, of course, you have a lot more complexity in there usually. But the good thing is that Dask knows exactly what depends on what and what can run in parallel. So it's a bit like Silk in that regard. So once you fire it off using the compute method, or if you explicitly refer to a result, then Dask will go and conduct all these or run all these different tasks in parallel where it can, and then deliver the results to you. So it's quite a nice way to implement a complex processing pipeline, I think. The other API that's something that we use for this particular project that I mentioned before is Dask Futures. You might have come across futures before in the context of Python itself. So Python implements futures as a parallelization package, and Dask basically re-implements that with the added benefit that you can scale up by using, say, the MPI backend and run this whole thing on a cluster. So the way this works is you typically have that for, say, a work sharing scenario where you have a whole bunch of data that you want to analyze. And so you define a worker function that operates on the data set, that does some processing of some sort. In the case of that consultancy, it was a machine learning job where the data gets analyzed using a training algorithm. And you then fire up Dask. You create a client, as you can see here, and use the map method that is also available in Python Futures to get Dask to call the worker function on every piece of data. And as soon as you do that, Dask will then hand off the data to all the different worker processes or worker threads, or depending on what kind of parallelization backend you use, and calculate. Then you just run through a loop. You pick up the results as they come in. So they can come in any order. Dask just runs whatever it runs in, whatever fits into the workers, depending on whether the different pieces of work are well balanced or whether some take longer than others. And one great advantage of this is that you can explicitly handle failures. I don't show that here on this little code snippet, but if you have, say, in a typical data processing job where sometimes you get data that's invalid, that crashes your data processing, you can explicitly handle that without bringing down the whole thing. So you don't have to lose all your results that you calculated before. You can just pick up those that failed and then process them later. And there are many more methods in the API that I don't show here. So you can send messages to workers, and you can do you have very fine-grained control over everything. So it's quite a sophisticated tool. Okay, so in summary, I think it's pretty easy to use. So as far as parallelization goes, you can go completely the lazy way and use one of these high-level integrated APIs, or you have to think a little bit about the parallelism and then implement it using the delayed or futures API. What you shouldn't use Dask for is something like a coupled weather forecasting model, something that Hillary mentioned before, or for CFD simulations, these kind of things. There's way too much overhead in the communication between the parallel workers, so this is not going to work very well. You could do it in principle, but probably not recommended. And one nice thing that you will see in Maxim's demo is Dask also comes with a nice dashboard, so you can check on the different workers and see what they're up to and how far they are through your workload. Okay, now let's jump right into Dask MPI. So as I mentioned earlier, the whole difference between Dask and Dask MPI is that Dask MPI implements the message passing interface at the back end. So those of you that have done HPC before probably know MPI very well. It's a library that allows different processes that run in parallel on an HPC to exchange data very fast. And that underpins pretty much every kind of large-scale modeling effort, like weather and climate simulation, CFD, and these kind of things. They all use MPI. So you don't actually have to know anything about MPI with Dask MPI. Again, it's all abstracted away. You just swap out the backend, and now you run on the cluster. It's a little bit rigid, so you have to have at least 3 MPI ranks or 3 MPI processes. If you try less, Dask will just get stuck. It won't actually give you an error message. It will just stop and not doing anything. And the reason for that is that in the setup, it needs 1 rank for the scheduler. So that's kind of the mastermind that keeps control over everything, that hands out work to the different workers, picks it up again after the work is finished, and restarts workers if they fail, these kind of things. Then you need a worker 1 that runs your script that has the, say, the Dask futures calls in it, or whatever you do there. And then you have at least 1 other worker that does the heavy lifting. And from there, you can scale up. You can have 1,000 workers or 10,000 workers if you like. So it's mainly geared at very large workflows, so that you don't suffer from having to spend at least 2 cores on things that don't do very much. So meaning the scheduler and the first worker. One good thing about it is that if you have a busy HPC like Higuera on NeSI, you can use this kind of method to fill in the gaps. So I show that in this little diagram at the top here. It doesn't matter where the workers run, you can just place them on all sorts of nodes across the cluster. And the way these clusters are usually utilized is that people run jobs of all sizes on it, and there are always little gaps here and there where a node is not fully used, and you can basically benefit and scavenge these idling cores, and so you get into the queue very quickly. So it's a very good way to harness the power of a busy HPC. So here's a performance result of what happens when you use such a scheme. So this is this consultancy again that I mentioned before. Here we combined scikit-learn, which itself is already parallelized. So scikit-learn uses multiprocessing and multi-threading. You can switch between those two to parallelize the machine learning tools. And we combined that with Dask, where we added parallelization over data sets. So the data sets were run in parallel, and each piece of data was then analyzed in parallel again with multi-threaded scikit-learn. And so in this diagram here, you see the performance comparison. The baseline is running 40 physical Skylake cores, which using hyperthreading translates into 80 logical cores on an HPC node. So at first only using scikit-learn multi-threading, and then combining that with Dask MPI, where I have in the first case, it's 13 workers, and then the scheduler and the first worker. And each of these, the workers runs with 6 threads for scikit-learn, and then a different mix on the right-hand side. And as you see, you get a 60% speed boost by combining this kind of parallelization. And of course, what I don't show here is that you get the ability to run on more than 1 node. So with Dask MPI, you can run on 100 nodes if you have as many as that. Okay, just a few technical bits. So for Dask MPI, you need an MPI distribution. There you need to pay a little attention to what is installed on the HPC or on the machine where you run in the cloud, say, or wherever else. So for the NeSI HPCs, we use Intel MPI, which is a derivative of MPICH. And so you need to, when you install Dask, you need to take care and choose the right MPI for Pi distribution. If you do that with Conda, it's pretty easy. It's just a matter of choosing the right channels, and then you can mix MPI for Pi with the correct MPI distribution and the Dask MPI package. And again, so Dask MPI is mainly useful for batch jobs. It is not really a tool that you would use for interactive jobs. This is something that Maxime's demo will show. If you have an interactive job, you might want to have a look at Dask job queue. But I don't want to steal his thunder, so I don't want to go into great detail here. Okay, so just very briefly, containerization. As I mentioned earlier, on a typical data processing task, you probably have a lot of additional packages and maybe some low-level libraries that you need to install, some executables that do some processing. So this can quickly get out of hand, especially if you want to be portable and run in the cloud or on the HPC. And so then tools like Docker or Singularity are your friends. And on the HPC, we can't support Docker, unfortunately, because Docker requires root access, which we can't give out to users. I don't have root access myself, so I'm also stuck with using a container runtime that runs without that, and that's Singularity. And Singularity also has the advantage now, thinking of Dask MPI specifically, that it provides very good MPI support. So there's it's specifically designed to keep the latencies low when you combine Singularity with MPI on an HPC. So when you, so I can't go into great detail here. We have a Singularity workshop on Friday afternoon, if you're interested in that. And there is a part with Dask MPI. And there I can show you a bit more about how to actually build a container with Dask MPI with using the Conda package manager. So here I just want to point out that running these containers is very simple. If you look at these two command lines here, you just slice Singularity in with between your MPI run and Python. And that means that MPI run will fire up Singularity, which in turn will spin up the container and then call your Python program inside. And the rest is all done automatically. So you don't have to worry about anything related to MPI, about the communication, and for all of this to work together, it's all done for you. And if you are using Slurm on the HPC, you just swap out your MPI run with srun and off you go. So the only thing that needs to be taken care of is that, again, the MPI distribution matters. So when you build your container,
sorry
you have
to
to be
interrupt
careful.
you, Wolfgang.
Yes?
We have 2.5 minutes left, and we have a few questions for you.
All right, okay. That's already my last slide. So thanks, Dan. So you just need to match your MPI distribution. So they're all not made the same. So just take care that where you want to run your container matters. And so unfortunately that is a bit against the portability aspect of it, but so you might have to create more than one container. Okay, just very quickly the summary. So I hope that I could show you that Dask is quite easy to use. You have to think a little bit about your parallelization unless you can use one of the high-level backends. And if you have very lightweight work, you have to keep the overheads in mind. And so again, there's a Dask demo just after this talk, and on Friday afternoon, we'll have a Singularity session that also includes a short bit on Dask. And thanks for listening.
Thank you, Wolfgang. Well, let's go through quick. First question, do the delay function have to be in Python, or can they be implemented in other languages? Does it rely on pickling?
So as far as I know, you have to at least the function wrapper in Python. So so you can then call a library from underneath, or you can probably run some syscall or something like that, or some shell tool from within that function. But I think the top level function has to be Python. So that the one that you hand over to Dask.
Thank you. Next question. What happens with Dask delay if one of these functions fails? Can you monitor progress of such workflow, or do you have to instruct the function yourself for that?
Oh, that's an excellent question. So with the Dask Futures API, I know for sure that you can catch errors. And so but I haven't used the Dask delayed API much other than just testing it a bit. But I suspect that you can catch errors as well. However, that of course then raises questions about what you do with the dependencies, because with Dask Futures, you don't really define dependencies. It all just runs embarrassingly parallel. So there's nothing downstream that depends on the output. Whereas with Dask delayed, there would need to be a way how to tell the rest of the pipeline what to do if something fails. So yeah,
thank you. We have 5 seconds left. And
right,
please go back to the timeline and see the pre-recorded demo of Dask. Thank you. See you soon. Bye.
Thanks, Dan.